Okay, so like I said, we have an exam on Thursday, a week from today, and we are going to be all ready for that. I know that you guys are going to do awesome on it, so I'm excited about that. And I know that you guys are as well. I need to share my screen, and the reason I need to share my screen is because I need to talk to you about what we're going over. Today, what we are going to be tackling is ideal gases. Um, we've previously talked about gases and gas laws. Most recently, or on Tuesday, we talked about acids and bases and determining different things about acids and bases. Um, Last Thursday, we talked about a couple of different gas laws, and today we're going to take those gas laws that we learned about last week and kind of consolidate them all into one kind of comprehensive thing. But before we do that, I want to go ahead and get started with a couple of starter questions. And so go ahead and do these poll questions. There's three questions, so make sure that you answer all three of them. And I'll give you another maybe 20 seconds or so to answer these. And I'm going to go ahead and close it right about now. And we're at now. Okay, so I'll share the results with you guys. Question number one, that looks pretty good. I'm nervous, but I'll get there. I'm happy to hear that. You'll get there. I agree with that. I think that you'll also probably feel quite a bit better after Tuesday. So after we've kind of had a bit more of a comprehensive review. If you missed this question, we still have more poll questions, so don't worry about that. The next question was kind of a review of last class period, where we talked about acids and bases, and we talked about two different definitions of, or theories of acids and bases. There is the Arrhenius definition or Arrhenius theory of bases, and the Arrhenius theory was that a substance that produces a proton would be is an acid. And if you remember, the Arrhenius definition had a bit of a deficiency, and the deficiency was that, well, it didn't really describe things like ammonia as a base. Ammonia is a base, but this definition didn't really qualify and didn't really clarify that. So that was a deficiency there. And so then about 40 some odd years later, there was the Bronsted-Lowry theory. Okay, so the Bronsted-Lowry theory, which statement best describes a base? And the most popular answer, so sorry, for question number two, the most popular answer was a substance that increases the concentration of hydrogen ions in solution. That is absolutely correct. So the popular answer was spot on. Great job. Then for question number three, according to the Bronsted-Lowry theory, which best describes a base? Well, a base accepts a proton. That is also correct. So if you remember, the Bronsted-Lowry theory is basically centralized around proton acceptance or donation. If something donates a proton, that's considered an acid. If something accepts a proton, well, that's considered a base. Now, I think that it's just to kind of give you a little bit of a primer. Let's say we have HCl. And whenever we look at a chemical reaction, I'm going to go ahead and stop the share of the results of this poll question. But everyone got those questions correct, so great job. Or the popular answers were the correct answers. So if we have HCl, that's an acid, hydrochloric acid. That will basically break down into two different things. One of those things is Cl minus, and the other is a proton. Okay, so when we read this from the left to the right, we could say that HCl donates a proton. Give me a one in the chat if you understand that we're meaning going from the left to the right. And it might be easier for you to visualize it as rather than saying donates, it releases a proton because I think that that's helpful because it's like HCl is one thing and then it releases the H, the proton that it has. Now, if I were to, okay, so it seems like folks are good on that. Let's go ahead and erase this. And now what I want to do is I want to imagine, well, actually, I'll rewrite that. HCl releases a proton and forms Cl minus plus H plus. Cl minus is Cl minus, kind of separating this off. If I write this reaction right here, um, would anyone, how would you, okay, so Cl minus moving from the left to the right to make HCl, how would you classify Cl minus? Would you classify it as an acid or a base? And think about it as, is it accepting a proton to reach this end or this final destination, or is it donating a proton? So is this an acid, A, or a B base? Tell me what you think on that. A for acid, B for base. The first two responses are opposites of one another, and so one of them is correct. Well, if we look at it, we're reading from the left to the right. If we're going from Cl minus and we are making HCl, well, then you could kind of think about it. What's the difference between Cl minus and H? Well, the H is the difference. So in order for Cl minus to become HCl, it has to accept a proton. And so anything that accepts a proton, like Cl minus here, that would be a base. Could you give me a 7 in the chat if that makes sense, or a Q in the chat if you still have questions? Okay. I think what's really helpful is to visualize this as, okay, I'm reading from left to right. What did I start with? What was that thing? And what does that thing become, more or less? Okay, so I'm happy that you guys are kind of still thinking on those topics, then those theories of acids and bases. Now we're going to kind of change gears a little bit and we're going to get into ideal gases. Now, if you think about, well, if you think about the term ideal gas, sort of presupposes or implies that there's a non-ideal gas. And that is correct. There is something that is a non-ideal gas. Now, ideal gases are the gases that you typically think about or that we will always be kind of talking about. And what I mean by that is they collide and they just bounce off each other. They just ricochet. This is not like one molecule of a gas collides into another and then they stick together. That is not the behavior of an ideal gas. Ideal gases, they will collide and ricochet, and they're not going to be like, so will not collide and stick to one another. That's kind of the most important thing that I want you to know about ideal gases. Now, if we move on, give me a 1 if all of this looks familiar. A 1 in the chat if this looks familiar, these equations here. Great. So these are all the laws that we learned about last Thursday when we were talking about relationships between pressure and volume and temperature, pressure and temperature, and then volume and amount. Now, one of the things that I am not going to ask you to know is I'm not going to ask you to identify gas laws by the by the namesake, I'll say. Um, what instead I'm most interested in is how do you do with the kind of conceptual understanding of this? How do you feel conceptually about this? And so what I've got is a series of poll questions that I want to give you guys, and I'm going to launch those right now. And it's a total of four questions. There's a total of four relationships here. Now, what I want you to look at is just to sort of think about these and plug numbers in. That I think is one of the most effective ways to address these sorts of problems. So if you think about the left-hand side versus the right-hand side of the equation, you could kind of think about it as initial state and your final state. And so what that allows you to do is kind of plug numbers in and say, okay, well, what if this variable changes? Because we only have two variables here. And so if we were to look at P1 V1 equals P2 V2, and while you guys are also answering your poll questions, I'm going to be working on this column right here. Now, the first thing is that if we have a pressure, let's say our pressure equals 2, the units that we're going to use are going to be atmospheres, or sometimes they're kilopascals. Now, what I want you to remember is 1 atmosphere is equal to 101.3325. I think I'll just go with 3. I'll otherwise define it. 101.3 kilopascals. But for this specific problem, this first one, I'm going to say, let's say our pressure in our initial state is 2 atmospheres. And let's say that we have a gas that has a pressure that's 2 atmospheres in a volume that is 3.5 liters. Now, if the pressure goes up, So now let's just say our pressure, our P2 is, let's say 5.2 atmospheres. Now, what is going to happen to the volume? V2 equals question mark. So what I'm going to say is 2 times 3.5. That is equal to 5.2 times V2. Now, this kind of indirectly will answer our first question, but we're going to actually go ahead and plug in the numbers to solve for this. V2, question is it going to go up? Is it going to go down? How much is it going to change? The first poll question says, when the volume of gas is cut in half at constant temperature, what happens to the pressure? It doubles, it stays the same, it is cut in half, or it increases but unpredictably. Well, I'm going to tell you that the answer option D, it increases but unpredictably, is not the correct answer. So what I'm going to do is I'm going to plug in 2 times 3.5. In this case, what happens is our pressure, well, it goes from 2 to 5.2, so it more than doubles. Now I've done 2 times 3.5, and I'm going to divide that by 5.2. So this is a little different from our poll question, but this is 7 equals 5.2 V2. I'm going to divide each side by 5.2, 5.2. So what has happened in this case is our pressure has gone up. So what happens to the resulting volume? Well, in our initial state, our volume was 3.5 liters. Now, when we do the algebra and say V2 is equal to 7 divided by 5.2, could you give me a Z in the chat if you're good with that, with this setup so far? Okay. So this situation is our pressure has gone up. What happens to our volume? Well, our volume is going to be 7 divided by 5.2, which is 1.35, I'm going to call it. So 1.35 liters. So our pressure goes up. What happens to our volume? Does it go up or does it go down? U for up, D for down. Well, it went from 3.5 to 1.35. So our volume goes down. Okay. Now, with that said, let's look at the structuring of this formula. We have two things that are multiplied by one another that are set equal to two things that are multiplied by each other. So this is the example of, is this an example of a direct, D for direct, or I for inverse relationship? A direct relationship is when one variable goes up, the other variable directly goes up as well. When one variable goes up and the other variable goes down, that's an example of an inverse relationship. So this first one is an example of an inverse relationship. Okay, now looking at the rest of the equations, are they all different from the first one? Give me a Y or an N to the chat. Yeah, they're all different, but then these three are structured in the exact same way. You're using, you're dividing a number by another number and setting that equal to a number divided by another number. Okay, so I always like to think about it as the first one here, P1V1 equals P2V2. That's multiplication. That is an inverse relationship. So way I think about it is multi, really underline that I, multiplication. So then I know that when one goes up, the other goes down. Now, these last three, would you describe those as, well, they're all division. Would you describe them as direct or inverse relationships? D for direct, I for inverse. Yeah, these are all direct. D for derision. I tried to say division and direct in the same word. This is direct relationship, and it is division. I don't write things going down very well, so I'll write it like this. So when you see this kind of structure, I think that that's helpful. Now, more directly and related to, let's say, question number 2 in your poll question, it reads, a balloon is warmed from 70 or 25 to 75 degrees at constant pressure. Okay. Let's see, at constant pressure. So what that means is that pressure is not a part of the equation. Well, a balloon is warm, so temperature is changing. What happens to its volume? Okay, so this second question is asking about volume and temperature. If temperature goes up, what is going to happen to the volume? U for up or D for down? Oh, I mean, heck, 76% said that it goes up. I'm going to go ahead and end the poll. So if you haven't answered, go ahead and get answers in quick. I'm going to end this poll. We can get these done. So that goes up. Now, question number 3. We can tackle this, and I'm going to share the results real quick. Question number 3 reads, a gas occupies 4 liters at 1.5 atmospheres. So volume is 4, and our pressure is 1.5 atmospheres. So 4, 1.5. If the pressure goes up to 3, what's going to happen to, or sorry. Oh, sorry, I was mixed up on this one. I was using the wrong one. A gas occupies 4 liters and the pressure is 1.5 atmospheres. Our pressure increases. What's going to happen to our volume? Well, our volume, great job, everyone. 60% of y'all said that 2.0 is the correct answer, and you're right. Now, the last question, and sorry, I'm going back to this third formula here. P1 over T1 equals P2 over T2. If our temperature goes up, our pressure is going up. And then our last one deals with amount of a substance and the volume of that substance. If the amount of our gas increases, what happens to our volume? Our volume is also going to increase. Now I'm going to go back to poll question number 4. A gas has a volume of 2.5 liters at 300 Kelvin. What is its volume at 400 Kelvin? Okay, so this is relationship between volume and temperature. Well, we can set this up the exact same way, 2.5 over 300. That is equal to 450 and V2. Solve for V2. So 250 or 450 times 2.5 is going to be like 1025. Divide that by 3, and you're going to get, I think the correct answer there is going to be that. Let me plug this in. 2.5 times 450 divided by, it's 1125 divided by 300. 3.75 is the correct answer. Okay, so the most popular answers were all the correct answers. So great job, everyone. Okay, so this is kind of a review of the gases. We're changing like one variable alone. Now, if we look at our next slide in this slide deck, this reads, and I want you guys to respond just in the chat. How do the particles behave when a gas is heated? How do these blue balls move? They're all kind of bouncing around. They're bumping into each other. The particles, do they move faster? Do they move slower? Does the speed not change? It's a pretty popular answer of A. They're going to move faster. And you know what? You're absolutely right. Those particles are going to move faster. So they're going to hit the sides of the container more often. They're going to collide with one another more often. Essentially, the number of collisions that are going to take place as this container is heated, those collisions are going to go up. Now, when it comes to gas variables and understanding gases, we've got 4 different variables. We've got the volume, 1 liter. Our standard unit is liters. That's what we're going to typically use. Our temperature is going to be measured in Kelvin. Our pressure is either 1 atmosphere or in kilopascals. 1 atmosphere is 101.3 kilopascals. And then last but not least is amount of a gas. Well, that is in moles, just like everything that chemists talk about is in moles. Now, what we need to kind of consider is, well, what happens if you add more gas to a system and you increase the pressure? So you change 2 variables. What happens if you change 3 variables? What's going on there? And that's what we're getting at today. What happens if we change our pressure, our temperature, and our volume? Well, there is an answer for that, and that is in the form of what's known as the combined gas law. The combined gas law takes the gases or the gas laws that we've previously talked about and the relationships between those and said, okay, well, we can relate pressure and temperature to one another. Pressure and temperature. Do we have that in one of our other gas laws? I'm going to change colors to this just so I can highlight it and, make it more clear. But the relationship between pressure and temperature, we've already talked about that. That's right here. If temperature goes up, then pressure goes up. Now, the other part of this combined gas law is right here, pressure and volume. Well, when pressure goes up, then volume goes down. Okay, so this essentially is asking you, well, what happens if temperature and volume both change? Like, what if the temperature, do you think that it's possible? Give me a Y or an N to the chat. Is it possible for the temperature of a system to increase and the volume to decrease? Is that possible? Think about it like this. Can you heat up a container and shrink that container, like physically? I mean, the way that I'm kind of visualizing it is if I got a balloon and I inflated it in a cold room, in a meat locker or something like that. I inflate it and then I take it outside where it's considerably warmer while I'm also I'm trying to shrink it with my hands. Is that possible? Y or N to the chat. Absolutely. So what does that mean for the pressure? Because The volume's going down, therefore the pressure should go up, and the temperature's going up, so the pressure is also going up. So those two things are working in concert with one another. Well, what if you make the volume go up, then the pressure should go down? We've got multiple variables that we're mixing around here. Could everyone give me a 5 in the chat if they follow, yeah, these two things, volume, temperature, and pressure, they all might kind of be at odds with one another. Okay. So this equation right here, the combined gas law, PV over T, addresses those sorts of changes. So an example of kind of a practice problem, a balloon filled with helium gas. And let me ask you this, or actually let me just share. I mentioned this last time, but I want to kind of double down on it. This says helium gas. The spoiler is that the identity of the gas does not matter. It could be helium, it could be hydrogen gas. It really is not significant, but we'll leave this here. Okay, a balloon filled with helium gas has a volume of 22.4 liters. Okay, so I'm going to put this 22.4 right here. And it is at a pressure of 1 atmosphere. And the temperature is 0 degrees Celsius. Okay. Now, just for consistency, what I'm going to do is I'm going to change this to 273 Kelvin because I like to use the temperature in units Kelvin. So I'm going to keep that straight. I'm going to do this so I don't mix anything up. Now, we've got two kind of practices. A is what is the volume of the balloon at 2 atmospheres? Okay, so our pressure is 2 atmospheres. The question is asking what is the volume? So V2 equals question mark. And then what if our temperature is -50? Well, if the temperature is -50, could somebody tell me that temperature in units Kelvin? Perfect. Thank you very much, Kelly and Victor. Great job. The temperature in units Kelvin is 223 because we added 273 to -50. So that's how we arrived at that. Now, if we look at these two things separately, if we look just at pressure, our pressure goes up. So what would we expect our volume to do? To go down, because those are inversely related. Pressure and volume are inversely related. But what about this other part? Well, our temperature goes down. If our temperature goes down, then we would expect our volume to go down as well. So in this case, the change in pressure and the change in temperature both contribute to the volume going down. Could everyone give me a 9 in the chat if that makes sense, or an S in the chat if that's confusing? And it is fine if you put 9S. It makes sense, but it's confusing. That makes complete sense to me, that it is confusing. So if we plug all this in, what we're going to get is, I'm going to use my calculator. 22.4 times 1 is 22.4. Divide that by 273. And that's going to give me a number that is 0.08205. I'm going to multiply both sides by 223. And if there's any point during the algebra that you get mixed up and you're like, why? Please don't hesitate to ask. So I plugged in 22.4 divided by 273. I get that. Now I'm going to multiply each side by 223. So that's gone. And now that gives me this number. So I'm going to plug this number. I'm going to write this out as the formula that I have. I've got 18.297 equals 2 times V2. I'm going to divide each side by 2. That's going to get rid of that. Divide each side by 2, and I get V2 equals 9.15. What are my units for this? What did I just solve for, and what are my units? Perfect. Thank you, Victor. Liters. So 9.15 liters. So that is my new volume. So, okay, this isn't too like mind bending or anything like that because, well, I knew that the change in pressure and the change in temperature would drive my volume down. Okay. Could everyone give me a 6+ in the chat if that makes sense? If what we did for this part A, you're good with that and you followed that. Okay. Now for part B, we're doing something that's almost the same, but a little bit different. So, what I'm going to do is I'm going to start out with my P1 V1 over P2 or over T1. That is going to be 1 atmosphere. I'm doing this at, well, I'm going to give myself a little bit more space. And actually, I'm going to give myself a little bit more space. Okay, so we've got, let's see, 1 atmosphere. Oh, nice light blue. That's a fun color. 1 atmosphere times my V1 is 22.4 liters. Divide that by my T1, which is 273 Kelvin. I'm going to set that equal to my new kind of state. My new state is the scenario that's described in part B. What is the volume? So I'm asking the same question. What's the volume of the balloon at 2 atmospheres? Okay, so my pressure didn't change. Or sorry, it didn't change from part A. So 2 atmospheres, V2. That's divided by my T2, which is 50 degrees Celsius. What should I record as my temperature? 323. Great job, Kelly. Okay, 323 Kelvin. So now what I'm going to do is I'm going to plug in 22.4 divided by 273. And I'm going to get that number right there, that 0.08205. I'm not going to write that out because I'm just going to save myself the space. I'm going to multiply each side by 323 Kelvin. Cross that out, cross that out. So now I'm going to take this number, multiply it by 323, and I get 26.5. I'm not done yet. 26.50, yeah, I'll stop at that, is equal to 2 ATM, 2 atmospheres, times V2. Divide each side by 2. I'm going to drop the units. Divide by 2. My V2 equals 26.5 divided by 2. 13.25. Units, liters. Okay. So what is this like? On the surface, you could look at it and say, oh, well, in both cases, the volume went down. Now, what I would interpret this to mean is, well, your pressure and in both cases, our pressure went to 2 atmospheres. Does everyone follow that? Give me a Y or an N to the chat. Okay. Now, the pressure alone, and this is kind of another, I need a follow up, and I want you guys to put an X in the chat if you follow this. Our pressure change alone, I'll say pressure doubling, maybe had a bigger impact on the volume than the temperature did. But what I want you to recognize is that the difference between this number right here and this number right here was basically a 100-degree temperature difference. Now, I'm not going to ask you guys to, and I forget the part about the X. I'm not going to ask you guys to like look at a number and say, oh, what was more significant, the temperature or the pressure? But I do want you to see the difference that, oh, okay, well, the temperature and pressure are additive. The temperature increasing right here caused the volume to go up, but not up from this 22.4, instead up from, well, 9.15. Now I'll ask, could you guys give me a B in the chat if you follow that and follow these two different scenarios? Excellent. Okay. So now I've got a pair of questions, a pair of poll questions. And these questions read, first one is, when using the combined gas law, which statement best describes how a gas behaves? A, a gas changes one variable at a time. Two variables can never change together. Okay. B, if pressure increases and temperature increases, volume must remain constant. Tempting. A change in any two variables will affect the third as long as the amount of gas remains constant. Okay. Now, just to compare, answer options B and C. B says pressure increase and temperature increase, the volume must always remain constant. It doesn't talk about how much they increase. That's one of the weaknesses in this option. Answer option C is a change. A change. My weight has changed in the past 10 years. It's gone up, it's gone down, it's gone up, it's gone down. Those are changes. So it's not it's increased or it's decreased, it's just it's changed. A change in any two variables will affect the third. Again, it's not saying that the third will go up or down, it's just saying that it will also change as long as the amount of gas remains constant. In this equation or in this scenario, it prompts you with a balloon filled with helium gas. Ooh, helium must be important. It's not. The identity is mentioned, but the identity is not important. But then we never bring it back up again. So that's one of the things. So then, sorry, final answer option, the law only applies to gases at low temperatures. Between these three options, C is your best answer option because a change, it's speaking, it's kind of like it's very political or diplomatic. It's saying a change, which could be positive or negative. A gas has a volume of 3 liters at 1.2 atmospheres and 300 Kelvin. It is compressed, so our volume goes down and our temperature increases to 360. What is the new pressure? Okay, so in this case, our volume is 3 liters, then it goes down to 2 liters. So volume goes down, therefore our pressure goes up. Volume goes down and our temperature increases. We've got two changes there. So what is the new pressure? In this case, you can go ahead and plug this all. I'm going to work this one on the next slide. And that's going to be an important place where we take off. P1 V1 equal or over T1. P2 V2 over T2. Okay, so we've got 1.2 times 3 divided by 300. Okay, so that's our first situation. That is equal to P2, which we do not know. That's what we're solving for. And our volume there is 2 liters. Okay, and our temperature is 360. So I'll plug this in. 1.2 times 3. 1.2 times 3 is 3.6 divided by 300 is 0.12. I'm going to multiply each side by 360. And I'm going to get 0.012 times 360. And I get P2 equals 4.2 or 4.32 liters. And I don't even have that as an answer option. What happened, Joel? Well, oh, yeah, I forgot to buy. Sorry. That is not the correct answer. I apologize, everyone. Much shame, much shame. Okay, so 1 point or 0.012 times 360 gives me 4.32 equals P2 times 2. Divide each side by 2, divide by 2, and I get 2.16. Our best answer option, 2.0. If this were on an exam, you'd have a better answer option, but D is our closest and therefore our best answer option. Okay, I'm going to go ahead and end that poll because now what we're going to do is we're going to transition to talking about, and I'll share the results. Answer option or question number one, C was the most popular answer. That's correct. D was the most popular answer on question number two. That was also correct. Now, we've got a little bit more to talk about. So we talked about our combined gas law, where we combined all of our gases. Now we have what's known as the ideal gas law, because we've got pressure when it comes to gases. Here's all the variables. This right here. We've got volume, pressure, and temperature. Those three variables are a part of the combined gas law. But then at the bottom in the lower right, we've got amount. Okay, so that's a fourth variable. So we have four variables. The combined gas law is combining several of those gas laws, three of them, to relate pressure, volume, and temperature. Our, but what if you know all of the variables except one? So all three of them except one. That's where we have what's known as the ideal gas law. The ideal gas law is PV equals nRT. Some people will shorten this and just say PVNRT, just to make it like a word for themselves. Um, Makes it easier to remember, I guess. And with this ideal gas law, we have a total of five variables. We've got P for pressure, V for volume, N for amount or moles, and then T for temperature. R is a new one. What on earth, R? This is known as the ideal gas constant. So essentially, this number, well, it is going to remain constant. It is not going to change, and it is going to have this value. Just so you guys know, you do not have to commit that number to memory. It will be helpful to recall it. I found it is most helpful to recall the units, though, more than anything else. Now, that number will be provided to you. It will also provide you with the units. But the reason that I'm saying I think that it's helpful to remember the units or the unit L times atmospheres divided by K times mole is then you can kind of figure out the structure of this. So, how does everyone feel about algebra? One being, I feel great about it. And five being, if I never heard the word algebra again, I'd be pretty fine with that. Okay. Well, for those of you who are friends of algebra or have no qualms with algebra, I just want to do one thing. And what I want to do is I want to take this equation, PV equals nRT, and I want to isolate R. So how would I do that? I divide each side by N and T, N, T. Now, I've rearranged this equation to be PV over NT equal to R. For those of you who, how do you feel about that level of algebra? Just rearranging an equation. One being, I feel good about that. Five being, oh my gosh, why, what happened? I quit. Nah, that's a little dramatic. I'm seeing ones, and I'm seeing ones from people who even put fives. Now, with that in mind, this is something that I think is a really valuable exercise because what I've run into problems with in my past is I'll be like, oh crap, I can't remember the units for this. Well, let me just take a moment and try to remember them. And this is helpful for me to sort of like reconstruct this number and kind of reason it out and say like there is a reason for this. What are the units? Somebody add to the chat. What are the units for pressure? ATM. Could somebody add to the chat? What are the units for volume? We're going with liters. So I just saw somebody at PSI. When we talk about pressure, we're not talking about pressure PSI like per square inch. We're talking about atmospheric pressure. Okay, so I've got P and V. I've got atmospheres and liters. What are the units for N or amount of a substance, amount of a gas? Moles. Okay, cool. And what about temperature? What do we measure that in? Kelvin. Perfect. Okay. Whenever I plug in those units, then I basically reconstructed ATM times liters over moles times Kelvin, which is the same effectively as that right there. Now, in the event that that was helpful, a simple little exercise, if that helped you and you're like, oh, okay, cool, I can follow that. That makes sense. Great. If you watched that and said, I don't understand why we did that, then don't worry about it. I will provide you with the number and the units, but I think that I always just like to do that just to kind of mental little gymnastics of sorts. Okay, great. I'm happy to hear that. And that was an instance where I was like, I kind of understand math after a long 20 some odd years of being like, math is bad for me. I'm not good at it. And as it turns out, that was just the internal voice that was telling me things that, well, it's not true. It's just things that I decide. Anyway, that's my philosophy portion of today's class lecture. Okay. So now before we proceed, could you tell me Y or N? Whenever I was talking about N, and any time we've talked about gases, I've defined them as ideal gases. Have I ever said, oh, the identity of the gas is super important, or the identity of the gas is even remotely relevant? No, never have. And you know why? Because it's not. So when we look at questions like this, A, what volume is occupied by zero point 0.5 moles of a gas at 1 atmosphere and 25 degrees Celsius? Oh, look at that. If I wanted to take this question and solve for volume, because that's what I'm looking for, I can take this equation, PV equals nRT, and divide each side by P. And now what I've got is V is equal to nRT over P. I know that this was a thing that my physics teacher always said. This is a phrase that she always used, but at this point, it's just plug and chug. You figure out the variables. This is my N. 1 atmosphere is my pressure. Temperature. What do I need to do with my temperature? Add 273 to it. So essentially what that means is I'm going to draw an arrow to kind of redefine everything. 0.5 times, and I'm going to plug in my R value. I'm not going to worry about units, even though I just kind of talked about units for a little while. 0.0821. And temperature, 298 Kelvin. Pressure, 1. I put Kelvin there just kind of a force of habit. I didn't need to. I can erase that Kelvin just as easily. I can erase that, move that in there. So whenever I plug this in and I say 0.5 times 0.0821 times 298, I get this number divided by 1, and that is 12.23. What are my units here? My units are going to be liters. Great. Okay. Now, that seems like, oh man, we had this longer equation with more variables. Is there more to it? No. There's not. There's no more to that problem. Does okay, let's kind of deconstruct this. What volume is occupied by zero point 0.5 moles of a gas at 1 atmosphere at 298 Kelvin? Um, what if I doubled the amount of gas? What's going to happen? Well, if doubling the amount of gas is the only thing that changes, then I'm looking at 1. And this number is effectively going to double to 22.4. What I wanted to really what I'm trying to demonstrate there is 5. Um, it doesn't matter if this question read 1 mole of a gas, 60 moles of a gas, or anything like that. Um, this is all there is to it. Now, this next option B says what pressure is exerted. So what we need to do is rearrange this equation to be isolating P. P is equal to nRT over V, or volume, 0 0.5 moles. So I'm going to go ahead and extend this out, say 0 0.5. I'm going to use my R value, which is 0.0821. And then I'm going to use my temperature, which my temperature here, still 298. And then my volume is 10 liters. Now, I'll plug all that in and I'll say divide by 10. My pressure is therefore going to be 1.223 atmospheres. One of the trickiest parts about these sorts of questions is really dealing with, well, what are the units? And you will see that as answer options. I could give you on an exam something like this, and I'll say A is 12.223 liters, B 12.2 or 12.23 atmospheres, C 12.23, and I'll leave no units, and then D, I'll throw a curveball and say 7. 7, I don't know, moles. So then it's really just up to you to say, okay, volume. What are my units for volume? Not atmospheres. I can measure units of volume, so it's not C. 7 moles, that's not it. So answer option A is my best answer option. Now, I've got a pair of poll questions that I'm going to back. Oh, stop sharing. I got to launch my next poll questions. And a sample of gas occupies 8 liters. So our V is 8. Our P is 2. And our temperature is 300 Kelvin. Okay. So I'm going to give myself a little bit of space and work on this. My equation is PV equals nRT. I'm going to work on 1 over here. 8 times 2. I'm going to use that as a rearranged PV equals nRT. What I am solving for is N. So I'm going to say PV over R, 0.0821. And if what I'm doing is confusing at all, please go ahead and tell me. I'm just trying to streamline this a little bit. So there is my R value, and my temperature is 300. So 8 times 2 is 16. Divided by, well, this is 0.0821 times 300. Okay, so that would be 16 divided by 24.63, because I went ahead and did this as separate things just because My function on my calculator isn't too advanced. 16 divided by 24.63, and I get the popular answer that everyone's provided, 0.65 moles. Now, question number 2 reads, a gas has a pressure of 101 kilopascals. Ooh, 101 kPa. This one does define 101.325 kPa as 1 atmosphere. So the first thing that we need to do is we need to take our pressure and we need to say, okay, we've been given 101. And we need to divide that by our defined conversion, which is 101.325. That's going to give me my number of atmospheres. So that's going to give me my pressure, 101 divided by 101.325. And I get 0.997 atm. So there's our pressure. Now, we've got a volume of 3 liters, temperature of 27. So I'm going to say T is equal to 300 Kelvin. Okay. Now, after that, what am I solving for? I'm solving for N. So I'm, again, kind of rearranging PV over, just want to make sure that I'm not missing anything in the chat. PV over RT equals N. So that would be RT, okay, sorry, 0.997 times my volume, which is 3, equals 2.991 over R, which is 0.0821, times my temperature, which is 300. You get 24.63. So 2.991 divided by 24.63 equals N, which is 0.12, which is the popular answer. 0.12 moles. Great. Okay, so that second question, there was a little bit more involved in that. The involvement was making that conversion, that first conversion from kilopascals to atmospheres. But as soon as you got that, then it's just take PV equals nRT and say, what am I solving for? Am I solving for N? Am I solving for T? What am I solving for? And then rearranging the equation to reflect that. So I'm going to stop the poll. The 2 most popular answers were the correct answers. So great job, everyone. I'm going to stop the sharing of that. And now I just want to do a little bit of reflection. And that is, we've got the ideal gas law and we've got the combined gas law. The ideal gas law is when you're given basically everything. So when the amount of gas, N, or the amount of moles of a gas is provided, and you are really just trying to solve one unknown, but you've got the other 3. So essentially, R is going to always be given. You have PV and N and are solving for T, or some other permutation where one of the variables, PV, N, or T, is unknown. The combined gas law, no N. No N is provided. No N is relevant also. Now, for both of these laws, you must have temperature in kelvins or in Kelvin. So what does that mean? I will always give you a temperature. If I don't give you the temperature in Kelvin, I'll give you in degrees Celsius. So you just add 273 to that. Now, next up is which of these problems, and you don't have to solve this because I'm going to have some closer questions in just a second. Which of these, add it to the chat, which of these problems requires using the ideal gas law as opposed to the combined gas law, A or B? So A reads, a balloon is filled with helium gas. Identity doesn't matter. It's gas. Has a volume of 22.4 liters. So V, a pressure of 1 atmosphere, and a T of 0 degrees Celsius. Okay, so I've got V, P, and T. It mentions the gas, but doesn't say how much. Okay, what is the volume? Okay, we're asking for V. So then if we look at B, what pressure, so P is what I'm asking, is exerted by 0.5 moles of a gas in a 10-liter container at 25 degrees Celsius. Ooh, okay, so we've got zero point 0.5 moles, so that's our N, V, T. So P, V, N, and T. So pressure is unknown. So everyone's chimed in with B is the correct answer, and you're absolutely spot on. Now I've got this slide right here, which kind of sums everything up. But before you go, I've got two kind of closer questions. After you've answered these, if you don't have any questions, I hope you have a wonderful Thursday. I hope you have a great weekend. Um, if you've got any questions about the upcoming exam, you can email me. We can join office hours at 11. Um, I will be on Tuesday going over basically a review of the exam in anticipation of the exam. And that's what I got. So thank you guys very much for coming to class. Thank you guys for engaging and participating. I hope you have a great weekend. I hope you stay safe, have fun, and I hope in any other class that you've got that you're, preparing for the exam. Our exam private message question next Thursday. So a week from today is when our exam's going to be. And I'll talk more about it on Tuesday, like timings and everything like that. So thank you guys very much. I'm going to stop the recording now, and I will see y'all later. You too. Here's my cursor. There we are. Oh, and I'll go ahead and actually, before I stop the recording, I'll go ahead and answer these questions. Which statement best explains the combined gas law, or what the combined gas law is useful for? It allows you to calculate moles of a gas. Nope. It predicts how a gas behaves when two or more variables change at once, as long as the amount of the gas stays constant. Yep, done. That's correct. If the amount of gas and temperature are kept constant, what happens to the pressure of an ideal gas when its volume is doubled? Okay, if the amount is constant and the temperature are constant. Okay, so PV and T. So the amount and temperature, we don't care about those. So do we need to use the ideal gas or the combined gas law for this? Let's think about this. When its volume is doubled, what happens to the pressure? Oh, this one's kind of tricky because I'll write this one out on the screen. There's a spider right in front of my monitor. Okay. Um, PVNRT. It's always tempting to be like, I've got to use all of these variables. But this question reads, if the amount of gas is constant, we don't need that. And the temperature is constant, we don't need that. The variables that we're talking about, P and V. So volume goes up. What happens to the pressure? Well, we've got this equation, Boyle's law, which is P1V1 equals P2V2. So when our volume goes up, that means our pressure has to go down. And we've got answer options A, pressure doubles, B, pressure is cut in half, C, pressure increases exponentially, or D, pressure stays the same. Now, I'm just going to go ahead and give myself some nice numbers. I mean, I think I've got a sense of what this is, but I want to give myself some quantitation of it. So, pressure of an ideal gas when its volume is doubled. So I'm going to say my pressure is 1, my initial pressure is 1, my volume is 2, equals P2 times, and my volume doubled, so I'm going to put 4 in place of V2. So that would be 2 is equal to 4 P2. Divide by 4, divide by 4. P2 equals 1/2. So our pressure went from 1 to 1/2, so our pressure gets cut in half. Okay, so the popular answer for that one is indeed the correct answer. So good job, everyone. Now I'm going to go ahead and end the poll and end the recording.